purpose of this activity is to introduce forces as vectors. Now we have dealt with especially velocity as a vector and position as a vector, so we already know how you can combine vectors using trig. But now in this activity we're going to introduce combining vectors using what we call vector diagrams. This is the setup that we're going to use to show force works as a vector. We have what's called a force table here. I'll give you a better view of that in a minute. We have 3 probes. This will actually be a person standing here. But with just me taking the video, I've got a really skinny person standing here. So this will be the resultant vector. It doesn't really matter which one of these I call the X or the Y probe. This is my resultant probe. This is I'll call this my X probe, and then this is my Y probe. We're going to keep the X and the Y probes at 90-degree angles to each other. So one will be our horizontal component or horizontal part of the force, just like we used to have. We've used Vx and Vy in our previous units. Now we're going to have Fx and Fy, and we're going to have this angle, and when I show the notebook, I'll give you another picture of how the angle relates. The angle we're going to measure is going to be the angle from, if I take the string from the X probe and I just would extend it as a straight line, this angle right here is the angle I'm looking at. Here's a top view of what the force table looks like. It's hard to get this focused real well, but you have 360-degree angles marked all the way around. We have a mark in the middle, and hopefully you can see that there's a string going. This would be my X vector, my X probe. This would be my Y probe. The angle I'm going to measure is this angle right here. I extend my X line and I measure this angle. So this particular picture, I don't know if you can read it, this says 40 from 90, so my actual angle would be 10, 20, 30, 40. I would call that a 50-degree angle. And you can spin this around any way you want, so if you wanted to, it probably makes sense to spin the 0 over here so it would be easier to read the angle. Here's a quick picture showing you how all 3 force probes are plugged in. It does not matter which one's in channel 1, 2, or 3, although you need to keep track of it. So you'll need to know which one's channel 1, channel 2, and channel 3. When you plug all 3 force probes into the LabQuest, this is what it looks like. You've got channel 1 force, channel 2, channel 3, and it will give you all 3 forces at the same time. When you take your data, you want your strings to be as close to the table as they can. It makes it easier to see what you're doing to the force table without touching and dragging on the table, and you'd like the string to go straight and not be at an angle, so this force would be measuring the straight pulling force. In this picture you can see how we're going to hang the weights. We're going to hang the weights on the bottom of the force probes. So this would be my X, the way I have it set up. This would be my Y. And the instructions say we're going to start with 200 grams in the X and 200 grams in the Y. We will leave the X alone. It will stay at the same weight mass, and we'll increase the mass of the Y by 100 grams all the way up to 600 grams. So I would start with putting 200 on the X and 200 on the Y. Then I would take my LabQuest and I'd read the forces and I'd read the angle from the top of the table. So in step 3, after I put the 200 grams on each of the X and the Y force probe, my goal is to get a picture that looks like this. And this picture probably doesn't have 200 grams on each, but I want a picture where I'm at a perfect right angle here. And to accomplish that, I'll have to adjust the person holding the resultant will have to adjust their position, and sometimes it's simpler just to adjust the table a little bit, but you have to keep this at a right angle. and then your lab quiz will read this force, the X force, the Y force, and the resultant force, and then you read that angle, and that's the data that goes in the table. And then you'll repeat that for the masses 300, 400, 500, and 600. And then there's some calculations you have to make, and I'll show you how to do that when I show you the lab notebook, which is coming up. Real quickly, I'm going to go over what I expect you to have in your lab notebook. I always want a title now. I want Introduction to Vectors Activity, and I do want this diagram in here. There's a picture of the lab notebook on the website, so if you need more time than this video has to draw that diagram, you can always go back to the picture and it'll give you what the whole page looks like. The data that you will have that matches mine or in the table are the 200s for the X mass and the 200, 300, 400, 500, 600. We just put that in grams for the Y mass. We really don't calculate with these. That's just so everybody's in the same ballpark as what your data will be. Then these are my pretend measurements. I've measured my force in the X, force in the Y, and my resultant force in the angle. Those things are what I measure in the lab, and I put them in the table, and of course you would have data all the way down. Then the instructions tell me to find the percentage difference between the sum of the squares of the components and the resultant. And I'll show you how I did that in a minute, and find the percentage difference, and then compare the inverse tangent with the angle and find the percentage difference. So using my made up data, and again, when I see your lab notebook, okay, I want to see this. I want to see the table. I should be able to see everybody's the same, so it looks really familiar. And I'm going to get pickier as time goes on and we all get used to the new system. So row 1 is the only one I have to show the numbers for. If you want to write them down for the other rows, that's fine. But if you want to just punch them in your calculator. So for row 1, all I did was square the value, the X force and the Y force, and I got a value. I squared my resultant, got a value. Then I took the percentage difference like we've been doing for several months now. I changed this because I kept one decimal because that's what we've been doing in this class. I divided by the resultant. So in both cases I divided by the resultant value, which is either the magnitude or the angle. And for my inverse tangent, it's fairly straightforward what I did here, and that's how you do the row 1. Then the instructions also tell us to do a vector diagram. Okay? So I decided to use 1 Newton for 5 centimeters because I only had 2 Newtons worth of force. So I changed that because if you use 1 Newton to 1 centimeter like the worksheet, your lines are going to be way short and it's really hard to be accurate that way. So the way I changed the Newtons to centimeters is you just set up a ratio and you put the Newtons on the bottom. So that means I need a 10.5 centimeter line for my X and a 9.5 centimeter line for my Y. So that's what I drew down here. I just made sure they were at a right angle, and then I just took a ruler and I measured my hypotenuse. That's the resultant, and I got 14.2 centimeters. Again, now I flipped my ratio, so I changed that back to Newtons, and then I compared that to what I measured on the table, which was 2.7. Found the percentage difference was 3.6%. You would do one of these. You're going to do 5 of these because you have 5 trials. If you want a little more detail, there'll be a part 2 of the video will be just on how to do the vector diagrams like you're going to do in your worksheet. So if you need more help, you can go watch that video now, or you can watch it later when you do your worksheet if you need help. Good luck in the lab.